Hello. In today's video we're going to be talking about solubility factors, so the things that are going to affect our solubility. Okay, so what allows a substance to dissolve in another substance, and how can we affect the amount that we can have in there? So first of all, whether or not something is soluble, or the extent of solubility, depends on intermolecular forces. So extent of solubility and or ability to be soluble, solubilized, depends on our intermolecular forces. Okay. Now with our intermolecular forces, we've looked at a lot of intermolecular forces in our pure substances, but there are a couple extra ones if we were talking about a mixture. So here are our different intermolecular forces that we have within mixtures. The first and strongest is an ion dipole, so that's going to be between a polar molecule, that's the dipole part, and an ion. So if we dissolve salt in water, an ionic compound in water, that is the type of force that we will see here. Next that we see, then ion dipole is only in mixtures. So this one's in mixtures only. And as you see from this, it's a very large energy force. Ion-ion interactions are greater. Dipole-dipole interactions or hydrogen bonding are weaker. So it's right in between those two. So generally we'll have ion dipole forces being introduced. Next is hydrogen bonding. Hydrogen bonding is 10 to 40 kilojoules per mole, so a weaker force. But it can be still pretty significant. Anything that can hydrogen bond generally will dissolve it in something else that can hydrogen bond. Next is our dipole-dipole. So if we do not have the ability to form a hydrogen bond, we will do dipole-dipole. So this is something that does not have a hydrogen attached to oxygen, fluorine, or nitrogen. So here again, this is a weaker force. So if we have two polar molecules, and again, this is, fairly similar in energy, or this is, if we have two polar molecules, they both have the ability to dipole-dipole, so if we add them together, we'll have that dipole-dipole interaction. So with these energies, this is the energies we're talking about. We're talking about our delta H of solution. These are the energies we would get back from that delta H when we put them together. So this is the solute-solvent interaction. So if these energies are on par with the solute-solute and solvent-solvent interactions, we'll have a solution form, but if they are not, then we will not have a solution form. So that's why intermolecular forces are so important here. Our next intermolecular force, and this is another one that is just in mixtures, is our ion-induced dipole. So if we were to take something like chlorine and place it into something like heptane, or sodium chloride and put it in heptane. Now, this is not likely. The reason that is because we have to break ion-ion intramolecular forces, and that is a very, very strong force, and all we get back is a very, very small interaction. So this is very unlikely to occur. Our next one is dipole-induced dipole. With dipole-induced dipole, we're going to have something that is polar plus something that is nonpolar. This is again in mixtures only and also not likely. This isn't likely, again, because we're talking about having to break dipole-dipole interactions or hydrogen bonding interactions as our solvent, and then placing in a very weak force. Okay. And our last one is dispersion forces. Dispersion forces are two nonpolar. And this is very likely to occur. Okay. With our induced dipole interactions with ion or dipole, like I said, those are not very likely to occur because of our delta H of solution resulting in very positive value because of how very little payback we get by making these solutions, how unenergetically favorable these are. But if we have a large enough induced dipole and a weak enough interaction between our ions or a weak enough interaction between our dipoles, sometimes it will occur. But generally, if you see a solution that the only option they have is ion-induced dipole or dipole-induced dipole, more than likely we will not form a solution. But just about all the rest of these interactions will occur in mixtures. So pay attention to the type of substances you have and see what type of intermolecular force you would form by making your solutions. So that's the first thing we're thinking about solubility. You have to have intermolecular forces that are similar in order to get a mixture to occur. But once we have a mixture, we can do some other things to affect our solubility. First is surface area. So surface area doesn't actually affect our solubility. It just will allow us to solubilize more quickly. So this gives us the speed of solution formation. Okay, and here we're talking about a solid solute plus liquid solvent. This is when we actually have surface area being an issue. So if we have our solid with a great amount of surface area, we are going to increase the rate of dissolution. It will not affect how much we can dissolve. It's just going to, if you have something like this has a greater surface area, so it's going to dissolve quicker. A block of sugar has a much smaller surface area, so it is going to be much slower. If you ever used a sugar cube, you probably know this already. Next thing we're going to look at is temperature. So temperature is going to have an effect on the extent of solubility along with the speed. So we're going to affect the speed of dissolving and the extent of solubility. Okay, if we are talking about with temperature, we can either talk about solid solute liquid solvent or gas solute liquid solvent. So we'll look at both of those in terms of the type of substance. Next one is pressure. So pressure is going to only affect gases. Okay, and we'll look at this again, but Henry's law. So, and specifically gases in liquid solvents. Okay, so we'll look at all three of those separately. So first, let's look at how those factors affect a solid solute plus liquid solvent. So if we have a solid solute and liquid solvent, our temperature is the first factor we're going to look at. As we increase temperature, we're going to increase our solubility. And we can look at this in terms of Gibbs free energy, delta G is equal to delta H minus T delta S. We can increase this term. Right, so as we increase our temperature, we're going to increase our entropy term, which will increase our Gibbs free energy, our negative value of Gibbs free energy, which will increase our solubility. In addition, greater temp results in more collisions, right, because our molecules are moving faster. So we're going to dissolve faster. Okay. Next, we're talking about a solid solute and a liquid solvent. Let's look at pressure. So pressure is going to have no effect on solubility when we have a solid solute and liquid solvent. Next, surface area. We already talked about this, but there's going to be no change on the extent of solubility. So it does not change the equilibrium solubility. But what it does is that it's going to change the rate of dissolving. So greater surface area, faster rate of dissolving. And that's again because we have more areas for collision. So a greater surface area, gives us more collision between our solute and our solvent. Okay. Next, we're going to look at a liquid-liquid system. So liquid solute plus liquid solvent. Okay. The only thing that's going to make any difference here are intermolecular forces. The other factors have no impact. Okay. Last, we want to look at a gas solute plus a liquid solvent. Okay. So, with temperature, as we increase our temperature, we're going to decrease our gas solubility. And it's because we have gas particles, and as they move faster, they're more likely to escape the liquid. Okay. So, our next thing for a gas solute plus liquid solvent is going to be pressure. And pressure, the greater the pressure, the greater the gas solubility. Specifically, we're looking at the partial pressure of our gas over our liquid. That's this whole idea of greater pressure, greater gas solubility is why we pressurize cans of cola to get more CO2 into the cola. And if you think about it, with a greater force above our liquid, in this case the force is the gas pressure, the harder it is for, or the easier it is for gas particles to penetrate the surface of a liquid, and the harder it is for them to escape. They're quite literally being pushed into the liquid. So it's easier for them to penetrate the surface, and the harder it is for the gas particles to escape. We relate gas pressure and solubility using Henry's law. Henry's law, like I said, it relates gas pressure and solubility and gas solubility. Okay, so Henry's law is S is equal to KH times by P. S is the solubility of the gas. KH is Henry's constant. And this is going to be for a specific gas liquid combination. Okay. If you change your gas or your liquid, the Henry's constant is going to change. Our last thing is P, which is our partial pressure of our gas. Okay. So our Henry's law is this one, but we can, if we have the same gas liquid system, we can set them equal to each other, and we don't want to change, so no change in temp. We're not changing temp here. Okay, but if we have the same temperature, same gas, same liquid, we can do a 2-point system of our Henry's law, and this is going to be the one we usually use. S1 over P1 is equal to S2 over P2. So if you know the solubility at a specific pressure, you can change the pressure and see what the new solubility is. Okay, and that's it for this. Bye, y'all.